And we'll talk about the Carnot engine, which is the most efficient engine. It's a reversible engine. It turns out all reversible engines are equivalent. It has the highest efficiency, and you can't do better than it, no matter how advanced you are. It just doesn't happen. Okay, so let's analyze a heat engine. So we take a heat engine and going through a process. So it's a heat engine, so you get we're using an ideal gas usually, and we're trying to analyze how much work and yeah.
Did you say that the efficiency was work done over heat lost?
It's the work that you get versus the amount of heat that you put into it.
Oh, okay.
So here is a heat engine. And so here is the figure. Here is the volume in cubic centimeters. This is the pressure in kilo pascals, and then I have here 200, and this is 200. All right, so the first, this is 1. Okay. It's initially there. That's the pressure and volume, and then it goes this way. It expands, right? It expands isobarically, and then the pressure drops. This is 3. Okay, this is 3. And this one is 600. And then it compresses isothermally. This is isothermal. This is isothermal, and the temperature is along this isothermal thing is 300 K. So first we would like to find when you're analyzing something like this, it's probably best to figure out what the temperature, pressure, and volume at every single point. And then you can find the work done and so on using the process. So it's probably best to find the temperature, pressure, and so on for each one. So let me write here at step 1. This is the step number for step 1. And then this is the pressure in pascals at step 1. This is the volume in cubic meters at step 1. And this is the temperature in Kelvin at step 1. Okay? So let's do this. And then step 2 and step 2. Okay. 2, 3, and this is the pressure, and this is the volume, and that's the temperature. So let's fill in what we know already. At step 1, what do we know? We know the pressure, right? You know the pressure, it's 200, right? The pressure at step 1 is 200 kilopascals. So it would be 2 times 10 to the 5th, right? So it's 200 kilopascals, and a kilopascal is 1,000, so 2 times 10 to the 5th. And then at step 1, the volume is 200. So it's 200 times 10 to the minus 6, because from cubic centimeters to cubic meters, you have to divide by 1,000,000. So it would be 2 times, 200 times 10 to the minus 6, that's 2 times 10 to the minus 4. And then the temperature, what's the temperature at 1?
300?
It is 300, yeah. Along this curve, anywhere here, the temperature is 300. So at steps 1 and 3, both of them have a 200 temperature. Not 200, 300. So step 1 and step 3, the temperature is 300. So let me just write that. At step 1, it is 300. And at step 3, it is also 300. Because they said it's isothermal. Now how about the volume? Let's see. We know the volume at all steps, right? At step 2, what's the volume? 600, yeah. So it's 6 times 10 to the minus 4. And at step 3, it is 6 times 10 to the minus 4 also. The pressure at step 2 is isobaric, so this is 2 times 10 to the 5th. Okay, so that's the pressure. So I'm missing 2 numbers. So I can find them. I can find first of all, the number of moles, and then I go from there. So the number of moles, I can say, and by the way, let's assume the gas is monatomic. Monatomic ideal gas. So N, the number of moles, N would be P1 V1 over R T1, and we can calculate it that way. So P1 V1, so this times this over T. Okay. So 10 to the 5th times 10 to the minus 4 is what? It's 10, right? 10 to the 5th times 10 to the minus, that's 10. And then 10 times 2 times 2, so that's 40. And this is 300, so 40 over 300. And 40 over 300 is?
0.13.
Huh?
0.13.
Okay, I will, 0. What?
333.
0.3. I got smaller than that.
Really?
40 over 300. So that's 4 over 30. Please double check.
0.133.
0.133?
Yeah.
Okay. Somehow I got 0.0. Oh, we didn't divide by R.
Oh.
8.31. Okay. We didn't divide by R. So,
0.016.
okay, thank you. 0.016. Yeah, thanks. All right, so P1 V1 over R2. So we found the number of moles. Let's find the pressure. I'm sorry, the temperature T2. So how do I get T2?
Yeah.
For T2, you will have P2 V2 over NR, right?
Yeah.
So T2. Let me do it here. T2 is equal to P2 V2 over NR. So let's do that. I will not plug in the numbers, I will let you do it. It should be a nice round number. Now, when you're doing heat engines, I recommend, to organize your thoughts, put a table. It's a good habit. Should be about
902.5.
902?
Yeah.
Yeah. So if you don't round the n at all, it's about 900.
Oh.
Yeah, I'll put 900. That's a nice number. So 900. And then the pressure at 3, we know 2 numbers, and so we can do the third one, right? So P3 is equal to N3, no, just N, R times T3 over V3. And I will give you a moment to also do that.
With 6.67 times 10 to the 4th.
I like that. 6.67 times 10 to the 4 pascals. Pascals, okay. Now next, they would like to know the work done, the heat added or taken away, and the change in thermal energy at each step of the process. Each, or at each process. So, let me put here process. And, yeah, 6 minutes, let's see. For 1 to 2. What kind of process is 1 to 2?
Isobaric.
Yep. So let me put here process name. So this one is isobaric. And then we would like the work done by the system, joules, the heat, and then delta E. Also in joules. Let's just name the processes and then stuff. So 2 to 3, and then from 3 to 1. So from 2 to 3 is what kind of process? Isochoric. And then from 3 to 1?
Isothermal.
Isothermal, yeah. The temperature does not change from 3 to 1. So isothermal. Are there any numbers that I can immediately write?
Work is 0 for the isochoric.
For isochoric, yeah, thank you. Work is 0 because the volume doesn't change. How about any other one?
For isothermal, the energy is 0.
Thank you. So these two you can just write right away. Now the other ones, they require some calculation. And so I think it's reasonable probably for me to just stop. And then next time we will start this product from scratch and then we'll continue on, okay? So just stop here. We have a quiz coming up.